Hello everyone, I'm Keisuke Sugiura from Keio University. In this presentation, I'd like to talk about a unified accelerator design for LiDAR SLAM algorithms for low-end FPGAs. I'd like to start by giving an overview of the SLAM. SLAM is the abbreviation for simultaneous localization and mapping. It is the task for creating a precise map of the environment and localizing the robot on this map. What you are seeing is the map of a building in the University of Freiburg and the trajectory of the robot. So a robot moves around the environment, collects the sensor data periodically, and creates a map like this one. SLAM is the basis for autonomous robots, and there exist many useful applications, such as navigation and house cleaning. SLAM has been an active research topic for more than 30 years, and LiDAR SLAM is well established and mature technique. But one major problem is that SLAM takes lots of computation and memory, and we need mid-range or high-end CPUs and sometimes GPU accelerations. For instance, cartographer, which is the state-of-the-art LiDAR SLAM method, is evaluated on a workstation with Intel Xeon CPU in the original paper. Another problem is that computational resources and the power budget are limited on indoor mobile robots. So it is usually difficult to use SLAM methods and achieve real-time performance on such robots. To solve this problem, in this work, we proposed an FPGA SoC-based LiDAR SLAM system for indoor mobile robots. Then we implement the system on PinkZ2, which is one of the low-end FPGAs. In the evaluation, we show the energy efficiency and real-time performance on real-world datasets. I will briefly describe some of the related works. FPGA-based accelerators are well studied in Visual SLAM methods. Visual SLAM uses camera like this as the primary sensor, and traditional image processing methods like feature detection, extraction, and matching are usually implemented on the FPGA part to boost the performance. LiDAR SLAM method is also widely used, but the computational cost and memory consumption are sometimes too much for mobile robots. And only a few works have considered the FPGA-based accelerators for LiDAR SLAM. So I will summarize the proposals and novelty in this work. We create a 2D LiDAR SLAM system on a low-end FPGA SoC, especially PinkZ2. This system can be easily integrated to various SLAM methods. We evaluate the system using some real-world datasets. We implement a robust and efficient SLAM matching method on the FPGA part. So in the next slide, I will briefly describe the SLAM matching method basics. Let's say we have a robot with a LiDAR sensor. LiDAR sensor emits laser rays and acquires the point cloud like this. Each point represents the surface of the obstacle around the robot. As you can see in this animation, SLAM matching tries to estimate the robot pose relative to the map. To do this, we need to maximize the overlap between LiDAR scan and grid map. Grid map partitions the environment into square grid cells. Each cell contains occupancy probability. The grid cells in this figure indicate the presence of some obstacles, like walls and furniture, and white grid cells indicate the free space. So the next question is how to measure the degree of overlap between LiDAR scan and map. I will refer to this as matching scores. To compute matching scores, we have to project SLAM points onto grid cells and then sum up their occupancy probabilities. We can say that SLAM matching is the problem to maximize the score by aligning LiDAR SLAM and grid map. We have so many SLAM matching methods. Now we are going to decide which one to use. Gradient-based iterative methods like gradient descent and Gauss-Newton are susceptible to local minima and requires good initial guess. But we need more robust methods to reduce the error accumulation in SLAM. Branch and bound methods try to find the pose by efficient grid search. Such methods perform pruning to improve efficiency and guarantees the global optimality. But high preprocessing cost and high memory consumption are the problem if we consider the FPGA implementation. So we will look into the real-time correlative SLAM matching, which is proposed by Olson in 2009. This method is basically the simplified version of branch and bound, and we will describe it in more detail. This method performs the efficient grid search to estimate the robot pose. It uses grid maps with two resolution levels and alternates between coarse and fine matching. This method is robust and guarantees the global optimality. It also performs the pruning to strip large part of the solution space to improve efficiency. And it doesn't have recursions, or it doesn't require any complex data structures, and only contains simple loops. We can also partially parallelize this method, as you see later. So this method is hardware friendly. And this animation illustrates the basic idea of efficient grid search. And we have a search window like this, and each point represents a robot pose. In the coarse matching stage, we roughly sweep the entire search window, and we rule out large part of the search window. In the fine matching stage, we sweep only the area of interest at fine resolution, and we find the final solution. In this work, we parallelize both coarse matching and fine matching in a simple and straightforward way. First, we'd like to see how to parallelize the coarse matching. I will just illustrate the basic idea and don't take a deep dive into the details. By tweaking and rearranging the loop, we obtain threaded accesses to grid map, as you see in this animation. We exploit these threaded access patterns. We then rearrange the order of grid map elements to make sequential accesses. In this way, we can partially unroll the loops and parallelize coarse matching. Next, we'd like to see how to parallelize the fine matching. The basic idea is same as the coarse matching. So we rearrange the loop and obtain sequential accesses to grid map. In the next slide, we are going to look at the details of the implementation. This figure shows the board-level implementation of the LiDAR SLAM system. We created a custom IP core for SLAM matching and implemented 2 IP cores on the FPGA programmable logic part. The design shown here is modular, which means that we can use these IP cores in various LiDAR SLAM methods without modifying and resynthesizing the logic part, as shown later. The SLAM matching IP core consists of a set of submodules, or HLS functions. The submodules here preprocess the input data, and the submodules here perform coarse and fine matching. We can transfer input data and receive outputs through AXI streaming interface. We can also write to control registers through AXI write interface to modify the behavior of the IP core. In this work, we integrate the FPGA-based stem matching accelerator into two well-known representative SLAM methods, namely a particle filter-based SLAM and graph-based SLAM. Both SLAM methods receive the LiDAR scans constantly and outputs the robot trajectory and grid map. But their approaches and internal workings are very different. So in the next slide, I will describe the details of the two methods and how to integrate the FPGA-based IP cores into these methods. A particle filter-based SLAM maintains a set of particles, and each particle estimates the robot trajectory and grid map independently. Therefore, we have to perform stem matching for each particle and throw away particles with unlikely estimates. Each particle is independent and there is no data dependency between particles. So we can use the two IP cores to parallelize the stem matching for particles. This means that each core repeats stem matching for half of the particles. A graph-based SLAM takes a completely different approach for estimating the robot trajectory and grid map. It is divided into front-end and back-end, and they work independently. The front-end periodically receives LiDAR scans and incrementally updates the robot pose by stem matching. The back-end performs loop detection and optimizes the robot trajectory. Loop detection tries to answer the question that, is the robot revisiting previously explored areas? And it is basically the same as front-end stem matching. So we can use one IP core for the front-end stem matching and the other IP core for back-end loop detection to improve the overall performance. We used PingZ2 as the target device, and the Vivado toolchains were developing the IP core. The operational frequency is set to 100 MHz. We also implemented graph-based and particle filter-based SLAM in C++ from scratch. We used several real-world datasets for evaluation. We selected 3 datasets from Radish dataset repository, namely Intel, MIT CSAIL, and ACES. These are sufficiently large indoor datasets. We also used Revo LDS dataset provided in the cartographer's website. This dataset is captured using the low-cost LiDAR sensor, which is mounted on the vacuum cleaner. We collected the sensor data at the campus building using the cart robots with Hokuyo LiDAR sensor. We first evaluate the FPGA resource utilization and power consumption. As you can see in the right table, our design with 2 stem matching IP cores is constrained by the VRAM resource available on the FPGA. And this is because we store grid maps on the VRAM memory to minimize the latency. However, we quantize the probability values in the grid map and also limit the size of the grid map up to 60 meters squared. So our design with 2 stem matching IP cores fits inside the low-end FPGAs like PingZ2. We also measured the power consumption of the entire PingZ2 board, and we confirmed that the actual power consumption of the FPGA part is less than 0.1 watt, which is a small value. We will compare the running time of the particle filter-based SLAM using 3 datasets. And we can confirm that the stem matching is a major bottleneck, and our proposed FPGA-based accelerator effectively removes this bottleneck. Stem matching part is accelerated by 13 to 14 times, and the overall performance is improved by 4 times. We also compare the running time of the graph-based SLAM frontend. We can see a 14 times speed up in the stem matching part for various datasets, and this allows up to 4 times performance improvements. This figure compares the running time of the graph-based SLAM backend. The time for loop detection is reduced by 17 times, and also the number of successful loop detections increased by up to 3 times. So the time for a single loop detection is reduced by around 20 to 50 times. We then evaluate the accuracy of the robot trajectory obtained in particle filter-based SLAM. As you can see in the right figure, we get almost the identical trajectory when we run SLAM in conjunction with the IP core. So we can confirm that the FPGA-based SLAM matching effectively improves the performance without compromising the accuracy of the outputs. We also obtain the similar results in the graph-based SLAM case. These grid maps are obtained using FPGA-based LiDAR SLAM implementations, and we can see that our implementation generates globally consistent and precise grid maps in various indoor datasets. We will also confirm that our proposed system satisfies the real-time constraint on other datasets. In other words, our proposed system can process the LiDAR scan as it comes in. We'd like to demonstrate our proposed LiDAR SLAM system on PINZ2. In this video, we accelerate 2 types of SLAM, graph-based and particle filter-based. Now we can see that the trajectory is optimized by the successful loop detections in the graph-based SLAM case. And these are the resulting grid maps. So let me summarize the contents in this presentation. We proposed an FPGA-based SLAM matching accelerator for 2D LiDAR SLAM methods. We chose to use real-time correlative SLAM matching and performed simple and straightforward optimizations to parallelize the SLAM matching. We implemented SLAM matching on a low-cost FPGA, especially PINZ2. Our design is modular and can be easily integrated to various methods. We integrated our design into 2 major approaches, namely graph-based and particle filter-based SLAM. We evaluated our design using multiple real-world datasets, and we confirmed that our design allows real-time performance on low-cost and resource-limited FPGAs without compromising the accuracy. So thank you for your listening.